Hello everyone, welcome back to the third lecture of week 9. The first and second lecture of week 9 has started with Taylor's theorem and Maclaurin's theorem, where we had seen some of the problems to solve using the Taylor's theorem as well as the Maclaurin's theorem. Maclaurin's theorem was the special case where taking A equal to 0 will give you, in the Taylor series, if you are take A equal to 0, that will give you Maclaurin's theorem. Here we are going to explore Taylor's series, not the theorem. So, series containing infinite terms. So, we are going to use that, and there will be some examples which is reflection of the application of this Taylor series. So, a Taylor series, now we will go through the basic definition. A Taylor series represents a function as an infinite sum of terms calculated from the values of its derivative and at a single point. So, what we are saying? We are saying that a Taylor series represented a function. So, f of x, right, and as an infinite sum. So, we are going from n equal to 0 to infinity, sum of the terms here, and all these terms are the derivatives at a single, at a point. So, that is the idea how to remember this one. So, Taylor series is nothing but it is just a function, and function is what? Function of the infinite terms, and those terms are the derivative of at a single point. Taylor series is a powerful mathematical tool used to approximate complex functions with an infinite sum of terms derived from the function derivative at a single point. These are the derivatives. So, all these terms are the derivative. Each successive term in the Taylor series expansion has a larger exponent or a higher degree term than the preceding terms. So, if you are writing f a, then next term must contain f dash of a, f double dash of a, and so on. So, each term containing that one has the larger exponent or higher degree from the preceding terms. So, now how to represent the Taylor series? So, Taylor series expansion of real and composite function f(x) whose differentiation exists in a closed neighborhood. Here the neighborhood is a, this one is f(x) is written as f a plus of x minus a. So, you are using a is given and n of a, that means the neighborhood. You want to find out the function properties in the neighborhood of a. So, let us say this x. So, how much the difference you have? You have a difference x minus a, right, either I mean negative or either positive, it does not matter. So, the difference is x minus a. So, f x now can be approximated. So, you can find out if you know the value f a and its derivative, that means f dash of a, f double dash of a, and so on, then you can approximate the value f x in terms of f a, f dash a, and f double dash a as just like a infinite sums. So, here f x is equal to f a x minus a into f dash a x minus a ka square divided by factorial 2 f double dash of a x minus a ka whole cube factorial 3 f triple dash of a. So, what will be the nth term? The nth term will become x minus a, this is the first, this is the second term. So, x minus a n minus 1 divided by n minus 1 ka factorial f of n minus a into n minus 1 into a, right. So, that will be the nth term of the Taylor series. So, how you can write this one f x? F x is nothing but you have to take n equal to 0 to n equal to infinity, and that will be your term. So, nth term. So, here f x is the complex or real value, n is the number of times the function is differentiable, and f of n represents the nth derivative of the function. So, Taylor series can be written as we had discussed here, right, n equal to 0 to infinity x minus a. So, here it is n equal to 0 to infinity x minus a power n minus 1 or n f of n n factorial. So, that is here I can write this n equal to 1 here. So, that is the notations we are going, and this notation is sometime it is called sigma notation, and it can be used directly as a formula. Since the Taylor series already contain the infinite number of terms, that is why it is taken as a sigma. So, how to prove that one? So, let A is the point in R be given. So, you are going to fix A here, and NA is the neighborhood, neighborhood of A, right, such that the function f has the n minus 1th derivative exist in where? On this neighborhood Na. So, in this neighborhood f of n minus 1 of the function, that means n minus 1th of differentiable function exists. So, then for any x belongs to n dash of A, n dash of A is what? N dash of A is a neighborhood except that point. So, what was the point? The point was A itself. So, therefore, the n dash of A I am considering as a delimited neighborhood, that means you are not considering A itself. So, f of x is equal to Pnx, fx can be written as, right. So, you had already A as a fixed point here, you have Na is the neighborhood point here, and you have a function here f, and this function is differentiable till n minus 1th derivative, right. So, that is the thing, you can write this or you can approximate this function as sum of the terms Pnx plus of Rnx of x, right, where Rnx is nothing but it is the remainder term after n terms, and Pnx is n minus 1th derivative. So, how many terms Pnx is? Pnx containing n terms. How many terms? N terms, 1, 2, 3 and so on, and the last term containing how much? N minus 1th derivative of that terms. So, now you can see there, the first term is f A, the second term f dash of A into x minus A, third term x minus A square factorial 2, and the last term of this Pnx is x minus A n minus 1 factorial f of n minus 1, right. So, using this construction of fx, where we had assumed the two terms fx as a Pnx plus Rnx. Rnx is what? After the n terms, whatever the terms may exist will be the remainder. So, Rnx is just denoted as a remainder. So, Pnx is a polynomial of degree n minus 1 such that Pna equal to Fa, Pna dash A equal to f dash of A. You can calculate by looking at the structure itself. So, Pna A is equal to what? All these going to be 0. So, this means f of A, right. Pna dash of A, Pna dash of A, that means you will get this term f dash of A, and Pna dash is f double dash of Pn n minus 1 derivative is f of n minus 1 derivative, right. So, Pnx is called the nth Taylor polynomial of f about a given point A. So, now this Pna by the structure itself, this Pnx is called nth Taylor polynomial of the given function f about a fixed point, about a point x equal to A, about a point A x equal to A, right. So, that is how we constructed our function in two parts. The first part is Pnx, the second part is the remainder one, and remainder where the remainder term contains after the n terms of the series, right. So, if a function f such that for each natural number n, f of n, that means the nth derivative exists on a neighborhood Na, then the polynomial Pnx for any x belonging to where? The delimited neighborhood, where the neighborhood is n of A minus of A. So, there is no A itself, right. Takes the form of infinite series as f A, x minus A, f dash of A, x minus A factorial t and so on, right. And let us say its name is 1. The question now arises that This series, how many terms it contain? It contain infinite number of terms, infinite terms, right? And does the infinite series converge? Your answer would be depending on the definition of a convergence of a infinite series. And what was the definition of the convergence of the infinite series? That was, we are looking for the partial sums, nth partial sums of the infinite series. The sequence of those nth partial sums of the infinite series, if it is convergent, the whole infinite series is convergent. If it is divergent, the whole series is going to be divergent. We are going to use the same thing. So, the first question is that does the infinite series converge? If it be convergent, does it converge to fx, right? The infinite series 1 will be convergent if and only if the sequence of partial sum. And what was the partial sum? Look at here, Pnx is the nth Taylor polynomial of about a. That means this is the partial sum itself. So, the sequence of Pnx will be convergent. If it will be convergent, the whole series is going to be convergent. In other words, if some of the series may be fx, the limit of the Pnx must be fx. And since fx equal to Pnx plus Rnx for any n, the series 1 will converge to fx if and only if this limiting value is going to be 0 here. So, that is our case. So, what we had done? We have done f of x is written as a Pnx plus of Rnx of x, and if I taking the limiting case, limit of Rnx of x equal to 0, that means Pnx as a sequence, Pnx as a sequence, if it is convergent, that will be convergent at f of x, right. So, that is the idea, and therefore, if I define a from a neighborhood of a, so Na is the neighborhood. So, if I define from this this particular neighborhood to R as a real function, such that nth derivative exists on Na for all n, then for any x belonging to some subset A, and what was the subset? Subset is here. So, you are not taking this A, and A is any subset of this n dash of A, right, for which limit Rnx, for which every remainder terms limiting is going to be 0, Rnx is going to be 0. F of x now becomes, so as you can see here, f of x is now becomes, since Rnx is going to be 0 here. So, this will leads to f a plus of x minus a f dash of a plus x minus a k square factorial to f double dash of a, and so on. So, that is the whole criteria. The infinite series on the right hand side is called the Taylor's infinite series for the function f about a point A. The region of convergence of the series is what? The A union of the singleton point A. So, let me give you the first example, and as you can see on the slide, find the expansion of the function f(x) equal to x cube centered at a equal to 2 using the Taylor series formula. So, you have to firstly remember that in the last we had the f of x about a point A is nothing but f a plus of the distance between x to a, this distance, right, f dash of a, that is x minus a k square factorial to f double dash of a, and so on. So, we have to find out f dash of x first, f double dash of x first, f triple dash of x. So, f dash of x equal to 3x square, this is going to be 6x, this is going to be 6, f of fourth of x is equal to 0, f of fifth of x is equal to 0, and so on, right. And we have to find at the centered a equal to 2. So, f dash of a equal to 3a square, and this will become f double dash of a equal to 6 into a, f triple dash of a equal to 6, f fourth of a equal to 0, f of fifth of a equal to 0, and so on, right. And now use the formula. So, f of x can be written as f a plus x minus a f dash of a x minus a ka whole square factorial to f double dash of a and so on. So, what is the f of x? F of x equal to x cube. So, we can find out f of x is equal to, this can be written as f a is what the f a? f a is equal to a cube plus of x minus a into f dash of a equal to 3a square, 3 into a square plus of x minus a cow square factorial to f double dash of a equal to 6 into a, and putting the value f x minus a ka whole cube by factorial 3, f triple dash of a is equal to how much? This is going to be 6, right? So, this is 6 and all other terms become 0, right. So, that will be your answer, but you had already fx equal to x cube. So, this means I will put the value, hold the value as a equal to 2 here, put the value a equal to 2. So, this f of x now become, or maybe I will write here. So, this f of x now become x cube is equal to a cube, that means how much? 8 plus of x minus a that means a equal to 2. So, x minus 2 into 3a square. So, 3 into 4 is equal to 12 plus of x minus of 2 ka whole square, and this is 2 into 6 equal to how much? 3 into a, 3 into 8 that means 6, and plus of x minus 2 ka whole cube divided by 3 into this will be cancel out. So, this will be your answer. So, now x cube is nothing but 8 plus of 12 into x minus 2 plus of 6 into x minus 2 ka square plus of x minus 2 ka whole cube. That will be your answer. So, now this fx is nothing but x minus 2 ka whole cube, 6 into x minus 2 ka square into 12x minus of 16, and that is what we have found out here, right. So, that is the whole criteria. You have to find out the derivative of a given function, look at the point where it centered, and that will be your answer. So, now based on the same criteria, the example 2, question 2 has been asked that find the Taylor series expansion for a function f(x) equal to sin x and x equal to pi. That means you have to given that with the pi x equal to pi, you have to find out the Taylor expansion of f of x, right. Doing the same thing, firstly I will find f dash of x, the first derivative f dash of x equal to cos x, f double dash of x that means minus sin x, f triple dash of x that is minus cos x, a fourth of this that means minus plus of sin x, and so on. So, now according to the Taylor series, what it will happen? F of x equal to f of a plus of x minus a into f dash of a plus of x minus a ka square factorial to f double dash of a plus of x minus a ka whole cube factorial 3 f triple dash of a, and so on, right. Doing the same thing. So, f of x equal to is given, f of x equal to it is given, f of x equal to sin of x. So, sin of x is now f a equal to sin of a, f dash of a cos of a into x minus a sin, and then f double dash of a sin a by factorial to x minus a ka square, and so on, right. So, put the value a equal to pi, equal to centered at x equal to pi. So, what is the value of a equal to pi? Now, putting this value sin x equal to sin pi cos pi factorial x minus pi is minus sin pi by factorial 2 x minus pi ka square minus cos pi factorial 3x minus pi ka whole cube, and so on, right. So, sin pi becomes 0 and cos pi equal to minus 1, and putting the whole value, it will comes out sin x can be written as minus of x minus pi plus x minus pi ka whole cube 6 minus x minus pi ka whole 5 by 120, and so on. Now, the question I mean, you can write down not in this way, but you can write down minus of x minus pi factorial 1 plus of x minus pi ka whole cube factorial 3 minus of x minus pi ka whole 5 by factorial 5 and so on, right. So, now you can have some idea that how the sin x will be explored infinitely. So, sin x can be written using the Taylor series expansion in such a way, right. We will see in a moment that what happen if I put a equal to 0, not a equal to pi. So, that will be also the good question, and it will comes out very easily. Now, look at question number 3, and it said evaluate the Taylor series for function f(x) equal to x cube minus of 10x square plus 6 at centered x equal to 3. So, since f(x) equal to x cube minus 10x square plus 6 and a equal to 3, find out f dash x. So, f dash of x, f double dash of a, f triple dash, and f fourth onwards is going to be 0, right. Put the value x equal to 3. So, f dash of a is going to be 3 into 3 ka square minus 20 into 3. F double dash of a is equal to 6 into 3 minus 20. F triple dash of a is equal to 6, and f fourth a onwards is going to be 0, right. So, that is using this thing you will find out f3 equal to minus 57, minus 33, minus 2, 6 and 0, and plug in this value fx. So, this fx is now become minus 57 plus of x minus 3 minus 33 and so on. So, fx can be written as in a direct value here x minus 3 ka whole cube minus x minus 3 ka whole square minus 33 x minus 3 minus 57, and that will be nothing but it is x cube minus 10x square plus 6. So, it is x cube minus 10x plus of 6. So, that is your answer, right. So, that is all. I mean, these problems are important problems where we had find out two polynomials equal to sum of the another terms using the Taylor series, and one trigonometrical function sin x can be written in a centered at x equal to pi can be written an infinite series. So, that is how the Taylor series play a significant role in writing in another word of the trigonometrical functions, and I believe that it will be good if we will explore more to more of such functions. So, here I had explored sin of x. Can you explore cos of x? And the answer must be yes, I believe so. You can explore it, and so take this assignment, right. In place of fx equal to f of x equal to cos of x at x equal to pi, So, find the Taylor series expansion of f of x. Since there are some time, so it will be good if I explore some of these values. So, let me explore this one. So, f of x equal to cos of x, therefore, f dash of x is nothing but minus of sin of x, and then f double dash of x equal to minus of cos of x, right, and f triple dash of x equal to minus minus plus, so this is equal to sin x and so on. Now, plug all those in here and put the value a equal to pi, and that will be your answer. So, as I have given you, you can try more and more complex functions using the Taylor series expansion, and you will see that one can approximate those functions in terms of the infinite terms. So, some of the infinite terms can be approximated for a given function in their neighborhood of a given point. So, thank you so much.